Hello, myself Naveen Saini. In the course Electromagnetic Field Theory, in the lecture number 11. So today we will discuss the next topic in the unit 2, that is convection and conduction currents and its properties. Along with it, we will discuss about the continuity equation. So first definition we will start from here, that is the current. So as we each one of us are aware about that, because this is our preliminary topic in our EMFT, that is the current. So current is nothing but the unit of this one is obviously ampere, and it is given by the electric charges passing through the given area or the per unit area. So okay, so this is also given by this expression I is equal to dq upon dt, or the change of rate of your charge from a given volume or a given surface area. So that is given by the term that is current. So this current we can discuss it into the material. So it can be of two types, convection current and the conduction current. So this depends upon the material on which the current flows, right? So in that, the convection current, it is nothing but this is the drifting of the lattice atoms into the material when we put it into the electric field, and convection current occurs into the materials like insulators, like rubber, liquid, gases, and so on. So convection currents come into that. Then second is the conduction current. So conduction current medium for that is your metals or copper, aluminium kind of things, so in which the conduction currents occur. So in that we have the current density. So the very basic definition for current density is this is the current flow per unit surface area, that is the current density. So this value is J is equal to delta I upon delta S. So if we want to calculate the total current passing through the surface, so that is given by the delta I is equal to J into delta S. So this is very important topic which we must know. So if in the question J is given, then and along with it we know the surface area through which it is passing through. So delta S, so this delta S can be into any of the coordinate system. It can be in the Cartesian coordinate system, cylindrical coordinate system, or the spherical coordinate system. So based on that we can find the total current passing through that surface area, right? So if we want to find the total current, so obviously what we will do, we will integrate this expression, and after integration we will get the I is equal to J dot delta S, right? So we can write it in terms of like this, or we can write it as the J into ds, right? Okay, so this is the I into delta ds. So few things which is we must know about that it does not involve the conductors and consequently does not satisfy the Ohm's law. This is the case of the convection current, because this convection current is flowing into the insulators, gases, okay, or liquids. So in that it does not follow the Ohm's law. So what is the Ohm's law? This is very simple. J is equal to sigma E, right? So because this is non-metal, so J sigma will not be there. So it means it does not follow the Ohm's law. It occurs when the current flows through the insulators, insulating medium or the insulating materials, and the other examples are the liquids and the gases or the vacuum. And another example of this convection current is the beam of the electrons in the vacuum tube. This is one of the very significant example in which the convection current flows. So here to find the convection current, so we have one of the elemental volume. So this is one of the elemental volume in which we have to find, and this is lying into the direction of y, and the convection current flows into in this direction, again in the y direction. Okay, so what we will take one of the volume, elemental volume like this. So we can take this one in which the surface area is for this surface, and delta y del y is in this direction, the y direction. So we can find the what is the current, right? Current flow into this. So current direction is this one. So how we can calculate that? Again we will apply the formula delta I is equal to dq upon delta t, And here we are very much aware about the delta Q, as we have discussed this in the unit 2 when we are talking about the Coulomb's law and the Gauss law. So delta Q is nothing but rho v into dV. So we have this feel of this topic already, how total charge can be calculated in a given volume. So it shows the total charge into the given volume, and that is delta V divided by delta T. So here we can also write this volume. Volume is nothing but this one, delta S into delta Y. So delta S into delta Y is the elemental volume. So the volume for this one is nothing but this is the del V, right? So in this case we can see that rho S into delta is there, and in this delta Y upon delta T is nothing but the velocity. So here we say this is the drift velocity, and the expression which it becomes, that is Jy, right? So Jy is in the direction of Y, right? So this is a Y component. So here we can say Jy is equal to rho V into Uy. So Uy is nothing but this one. So in general we can find for all other cases that J is equal to rho V into U. So this is the convection current density, rho V into U. So here when we talk about the conduction current, so the requirement for conduction current is what? These conductors are required, and one of the difference between the convection and the conduction current is what? Here in the conduction current we have a large number, or the abundance of the electrons into the material, right? So this is the second point in that. And as I said, when the large number of charges are there, if the charges are there, it means the electric field will be there, and in that case the force exerted onto one particular charge is equal to E into, so as we know, the electric field is nothing but the F into Q, right? So when we talk about the force on an electron, so in this place of Q we can write the minus of E charge, right? So this will become F into E. So F is equal to E into small e into capital E. So in the free space the electrons would accelerate obviously, and into the materials the electrons suffers continuous collisions into the material, and this electron will move with the different velocity between the collisions. Okay, when we have different collisions occur into the between the atoms, so in that case the electrons movement will be can be find out based on the different velocities. Every electron will have a different velocity. Okay, so in that we can, as I said, the every electron has different velocity. So in this way the average velocity can be find out with the help of this term, that is the drift velocity U, and this is nothing but U is equal to minus E tau upon m into E, right? So this is the formula for that, and where tau is what? This is the average time between the collisions, right? And m is the mass of the electron. Drift velocity is directly proportional to the applied field. So here we can see that the field drift velocity is directly proportional to the E, because for E is constant, tau is constant, m is constant for the electrons. So in this case the U will be directly proportional to the electric field or the applied electric field. So here if we have n number of electrons per unit volume, so in this case the rho V will be equal to minus of n into small n into E, right? So okay, so here we know the formula which we had derived for the convection current. So it means here this is a general formula where we can put the value of rho V or U, right? So rho V, we are aware about that. Rho V is nothing but the minus n into E. What is the meaning of this rho V? This is the total charge present into the given volume, right? So if we have n number of charges are present into the volume, so an electron is E, so we can say this is the minus n into E. So the total number of charge density. So in place of rho V we can put the n into E, and in place of U we can put this expression. So when you put all together, then we will get the n e square tau upon m into E. So here we can say this is equivalent to the sigma. So this sigma is nothing but the n e square tau upon m, so which is the conductivity of the metal or the copper, any of the material in which the conduction current can occur. So here J is equal to sigma into E. So this is the nothing but this is the Ohm's law, right? So this is Ohm's law. Clear? So this is the Ohm's law which we will use when we go for the continuity equation into the material. Next point in the conductor, we will have some of the property of the conductor is what? A conductor is nothing but which have the large number of electrons or the which are free to move into the material. So this is the basic property of the conductor. But when we have the perfect conductor, so for that the sigma value will be very large, or sometimes we say the superconductor, that is the sigma is equal to infinite, or the perfect conductor. Okay, so which cannot an electrostatic field within it. So this is the point in which, right? So what is the meaning of this? So when we have any of the conductor in which the electrons are uniformly distributed, so when we put the this complete conductor into the electric field or external electric field, so this case is very similar. It's like that when we have this type of conductors, right, and this is connected with some of the external charges. So in this case the current will flow into it, right? So the very simple fashion we can say, when the current is flowing into it, it means it is into the electric field. So here when we put it into the external electric field, so what will happen? So there is accumulation of the positive and negative charge in one of the side on the onto the conductor. So when we put this conductor, this is the conductor, when we put it into the external electric field, what will happen? The positive charges which is within the surface, within the conductor, it will be accumulated on the surface towards the electric field, right? And the negative charges, this will be accumulated opposite to the electric field surface, right? So within the within the conductor, the direction of electric field will be what? Positive to negative, right? So as we know, the positive charge will emanate the electric field, and the negative charge, that is disperse, or sorry, you can sink the electric field into it, negative charge. So the direction of electric field within the conductor will be plus to minus sign, and external it is this way. So we can see again here it is a EE in this field. So we can say the direction of the electric field within the conductor is opposite to each other. So it will cancel out to each other. So in that case, what will happen? The electric field will be 0 within the conductor. So when the electric field is 0, so in this case, when the electric field is 0, it means there is no charge present within the conductor. So it means the rho v is equal to 0. So rho v is 0, it means the potential will be equipotential, or the potential will also be 0. Okay. So we can say there is no charge present within the conductor. So all the charges will be present at the surface of the conductor. So we can see it like this. Okay. So within the conductor there is no charge. On the surface there is the charges are present into the material, metals, right, or the conductor type of metals like copper. So that is why whenever when we have the wire, conducting wire, so within at the center of the wire there is no current flow, so we cannot feel any current in that. Okay, so current always flow at the surface of the conductor, always, right? So we have to take this point into our mind. So when we go further, okay, so inside the conductor, same thing which we have discussed, this value will be 0, rho is v is 0, this is equipotential body. Okay, so we call it the conductor as the equipotential body. So when we have this type of formula, that rho into E dot ds, so this is nothing but this is very similar when we have the D dot ds is equal to rho v into dv. So in place of d we can put the epsilon e. So in this way this will become the epsilon e, and ds rho v into 0. So we have rho v is equal to 0. So if electric field is 0, the rho v will be 0. So inside an isolated perfect conductor, electric field rho v and VAB is 0. So VAB is nothing but this is the potential difference, right? So VAB is potential difference between the 2 points A and B in the conductor. So equipotential surface, the potential will be same within the conductor, but the potential difference will be 0. Then we have another concept of in the electric field, that is a polarization. So polarization is very much aware to all of you that when we have the charges present into the material, so in that case, so as we said about the conductor, right, within the conductor the electric field is generated within the conductor, and they will cancel out with the outside electric field, right? But in the case of dielectrics, because this is not the perfect conductor, this is not the insulator, so in that case the movement of charges will be lesser as compared to the conductors, but it is more than insulators. So in the dielectric materials, what happens, the charges are not able to move about freely. So if the charges are not freely movable, just like in conductors, so this is the dielectric. This is a very simple phenomenon in that. So they are bounded by the finite forces within the lattice, and the displacement will take place when external force is applied or external electric field is applied in that case, right? So the atoms or the molecules are electrically neutral since positive and negative charges have the equal amount. Next point in that is the electric field is applied, positive charges move into direction of electric field and negative charges move into direction of opposite of that electric field, just like the conductors, right? The same phenomena occur. So what will happen? So as we put this material or the atom into electric field, so what will happen? The nucleus of this will be in this direction, in the direction of electric field, and negative charge which is around to this around the nucleus, it will be accumulated at the left hand side of that, so opposite of the electric field. So here this is the dipole which is generated. So in the cloud of electric charges, we say this is the minus q charge, and the cloud of plus q charges are nothing but positive charges are plus q charge. So this forms the one of the dipole, right? So plus q is the nucleus and minus q is the electron. So that is equivalent to that when we put it into electric field, so positive charges and the negative charges. So how these things will be occur into the system. So in that we have a dipole moment. This dipole moment is P is equal to Q into D, where D is the distance vector from minus Q to plus Q of the dipole. So one of dipole occurred, and here if we have n number of dipoles, so obviously it will be Q1 D1 plus Q2 D2 plus Q3 D3 and so on, Q1 Dn, that is equivalent to the summation of k is equal to 1 to n Qk dk. So as a measure of the intensity of the polarization is occurred, and it is defined by the Q into D per unit given volume. So for that one we have the polarization formula which we can take care of. P is equal to Qk dk divided by the delta V, and delta V tends to 0. So at every dipole we have the polarization, and this polarization will take place in the two ways. First one is a non-polar case and second one is the polar case. So what is the difference between these two? So in the non-polar dielectric molecules which does not possess dipoles until the application of the electric field, right? So the example for that one is the hydrogen, oxygen and the nitrogen. So these are the cases for non-polar cases. Polar cases are there where the molecules have built-in permanent dipoles, right? This is very important point, and that are randomly oriented. But when we put it into the electric field, they will be aligned, right? So these things are mentioned here. So example for that polars are water, sulfur dioxide, right? H2O or SO2. So here it shows in the figure A, when there is no electric field is applied, then in the polar case the dipoles will be formed, it will exist, but when we but these are not aligned in one direction, so it randomly it can move anywhere. But when we have the when we put it into the electric field, so what will happen, this will be aligned, so positive charge and the negative charge like that, right? So this shows the polar cases where the permanent dipoles are already formed, but non-polar there is no permanent non-permanent dipoles are formed, right? So in that we have the some of the formula which is important. If you interested, you can go through. The dipolarization occurs when two charges densities are formed, right? So in that the equivalent surface charge density, that is P rho PS is equal to P into AN, right? And in that we have the, in terms of the gradient or divergence, we can put it rho P rho is equal to minus del into P, right? So this rho PS and rho PV, that is called the bound surface and the volume charge densities, right? So rho, as we are aware, rho V is the volume charge density and rho S is the surface charge density respectively. So there are distinct free surface and the volume charge density which is given here, and the bound charges are those that are not free. They are not free to move within the dielectric materials. So they can be caused by the displacement that occurs on the molecular scale during the polarization. So these are the some of the important aspects about the polarization into the dielectrics. Okay, so but please go through it. So one of the few formula for that which you had to take care of about polarization dielectric. So this is the rho t is equal to rho v into rho v plus rho pv, right? And when we do some of the calculation or some of the rearrangement of this formula, then in that case we will come to this expression, right? D is equal to epsilon E plus P. So what is significance of this one is simply when we have the free space, then in this case D will be equal to epsilon naught E. Okay, so this is the case for the free space. But when we have any other material, any material in which or the dielectrics, so in that case we have to add one of the factor, that is the P or the polarization. So okay, so D is equal to epsilon E plus P. So P is nothing but this, the P is equal to psi E epsilon naught into E. So we can put this value here. So in this case D will be what? D will be epsilon naught into E plus psi E epsilon naught into E, right? So we can take it out like 1 upon x E into epsilon naught E, right? So here psi is what? This is the susceptibility of the material. So when we put it into the any external applied electric field. So this is very simple. 1 upon psi, we can say this is epsilon r into epsilon E into E. So we can say this is equivalent to epsilon into E, right? So very simple. In this case, epsilon r is equal to what? 1 plus psi E, and epsilon naught is same, and epsilon is nothing but 1 upon 1 plus psi E into epsilon naught. So same thing is mentioned here, that D is equal to epsilon E, and epsilon is nothing but epsilon naught into R, epsilon R, and epsilon R is 1 plus psi E, or we can say in another word epsilon upon epsilon naught. So here the epsilon is nothing but this is the permittivity of the dielectric. Okay, and epsilon naught, this is the relative permittivity. Epsilon naught is the permittivity of the free space, and epsilon r is the relative permittivity. So here we know the formula for this. Epsilon naught is equal to 10 to the power minus 9 upon 36 pi farad per meter. So here the dielectric constant, that is epsilon r, is the ratio of the permittivity of the dielectric to that of the free space, right? So here this is mentioned about the how dielectric field occur into it, and there are different cases of that which we can discuss it here, that when no dielectric is idle, right? So when the electric field in the dielectric is sufficiently large, so it begins to pull electrons completely out of the molecules, and the dielectric becomes conducting. Okay, so dielectric breakdown which occurs when the dielectric becomes conducting. So this is the in between the dielectric is nothing but this is the in between the insulator and the conductors, right? So when the electrons are bounded bounded and are not movable, so in this case this is the go through the insulators. But when we have free electrons and it is large enough, it is come into the conducting nature, right? So dielectric strength, this is maximum this is the maximum electric field that a dielectric can tolerate, withstand without electric breakdown, right? So this is some of the cases which we have just discussed about the dielectric cases and the polarizations. So another property of dielectrics which we can go through it about the materials, that is the linear, isotropic and homogeneous dielectrics. So what are the some definitions for that? We can go through it. So when the material is linear, it means D varies linearly with the dE, right? So it means D is equal to what? This is the epsilon into E. So when a material is linear, in this case epsilon will become epsilon naught. So D will be epsilon naught E. So here materials for which epsilon does not vary in region being conductors, okay, being considered. So if epsilon is uniformly, this epsilon is not changing from one when we are moving into the material one point to another point. So in that case, it is the case of the linearity of the system, or we say this is in the homogeneous medium, okay, linear medium and the homogeneous medium. Then what is the inhomogeneous? So materials are inhomogeneous. What is the case of that? When epsilon is dependent on the space coordinates. So it does not, I mean, it depends when we are moving into a Cartesian cylindrical spherical coordinate system. So in that systems, epsilon can be changed from one point to another point into a given area or the space. So materials for which D or E are in the same direction are the isotropic. On anisotropic, in which material D, E and P are not parallel, or epsilon or psi E has the 9 components. So we are not going into this in detail because this is not relevant for our syllabus right now. So please just take care about this of these things like linearity, homogeneity, inhomogeneity, and isotropic. So these are the cases which you have to take care of. So linear isotropic homogeneous dielectrics, so which shows the formula for that when we have the homogeneous cases. So here dx, dy, dz. So this is a basic formula for this epsilon into E. So d we can write in the Cartesian coordinate system, epsilon is in this coordinate system. Epsilon we can write in all the directions of x, y, z, and electric field we can define it like this. So a dielectric material is linear if d is equal to epsilon E and epsilon does not change with the applied electric field. This is a very important point. Then we have dielectric materials in which it is homogeneous if d is equal to epsilon E, and in that case an epsilon does not change from point to point. Third one is the isotropic in which d is equal to epsilon E and epsilon does not change with the direction. Okay, so these are the properties of any of the material when we take electric field or electric flux density into the account. Now come to another topic, that is continuity equation and the relaxation time. So for that we have to go through one of the basic principle about the continuity equation, that is the charge conservation. So in that charge conservation, what will happen? This is nothing but the rate of decrease of charge within a given volume. It must be equal to the total current out from that surface or from that volume, right? So as we said, if this is the volume in which the charges are present, right? Some charges, all these are present. So at what rate the charge are decreasing from this given volume is equivalent to the current out from that volume. So we can define it, I out is equal to, so we can define it as the I out is equal to Q in divided by the QT, right? These are the basic definition of the of that principle, charge conservation. So in place of I out, what we can write, that is J into ds closed surface is equal to minus dq in upon dt. I think this point is clear, right? I out we can find write J dot ds, and here we can use the divergence theorem. Apply कीजिए, then in that case what we will get, the J dot ds that is equal to del dot J into dV. Okay, and in place of Q in we can write the integration rho v into dV. So we will take these things, right? So here we have put it all this all together. So Q in we put the rho v into dV. Okay, in place of J dot ds we put the del dot J into dV. So when we equate these two equations, so this after this we will get this, and here we can compare these two equations, then del dot J will be equal to del rho v upon del T with a minus sign. So here del dot J is equal to minus del rho v upon del T. So this equation is called the continuity of current equation or the continuity equation in the for in the material, right? So this thing, this continuity equation is helpful to understand about the how when we put the charges within the substrate, so how it disperses into the substrate. So this phenomena can be taken care by this equation. Okay, so second part of this derivation of the continuity equation is when we are introducing the charge at some interior point of a given material. So we will use three formulas for that. First is the Ohm's law, which we have just covered. Gauss law, that is del dot D is equal to rho v, and the del dot E is equal to rho v upon epsilon. Okay, so simply just take this example. Del dot J is equal to minus del rho v upon del T. So in place of J, simply put the sigma E from here. Then just rearrange the things. So when we rearrange it, so very simple is this one, we can use this here. I will write it, J is sigma E is equal to minus rho v upon del T. Okay, so in this case, del dot E is what? Del dot E is rho v into epsilon into sigma is equal to minus del rho v upon del T. Okay, so the same thing is mentioned there, that del rho v upon epsilon divided is equal to minus del rho v upon del T. So just rearrange the things, and this is nothing but this is the homogeneous equation, linear homogeneous equation. So the solution, because it becomes here, so this is the equation. So if we want the solution of this equation, so for that case, what we have, simply we can use a linear homogeneous equation, like if you remember the del dot del upon del T, we put the D. Okay, so this is the D plus sigma upon epsilon into rho v is equal to 0. So when you solve this equation, so roots of this equation is D is equal to minus sigma upon epsilon. So in this case, rho v equation will become rho v naught e to the power minus sigma upon epsilon into T. Okay, right. So here in play, okay, so this is the equation which we got, and here we can convert this rho v is equal to rho v naught e to the power minus T upon TR. So what is the TR? Here TR is epsilon upon epsilon T, epsilon upon sigma, right? So this is nothing but this is the transmission relaxation time, right? Epsilon upon sigma. So TR is the time constant in seconds, and rho v, the equation will become rho v is equal to rho v naught e to the power minus T small t upon capital TR. So this TR, it signifies the relaxation time, and the definition for this relaxation time is nothing but this is the time it takes for the charge placed in the interior of the material to drop to 1 upon e to the power minus 1, or 36.8% of the initial value. So how we get this this point? Here, if we go back here, right? So for this, at T is equal to 0, rho v is equal to what? This is rho v naught into e to the power 0. So this will become rho v is equal to rho v naught, right? So this is the case when T is equal to 0. So when we just inject the impurity into the substrate, right? So at this instant, rho v will be the initial value of that one. At T is equal to TR, right? So at the time of relaxation time, that is TR. So in this, rho v will be equal to rho v naught into e to the power minus small t. In place of small t, we can put the TR. So TR divided by TR. So this value will be rho v naught into 1 upon E. So when you find this 1 upon E, so 1 upon E is E is what? 2.7. So 1 upon 2.7 into E so okay, so into, sorry, this will be rho v naught. So 1 upon 2.7 is 0.368 into rho v naught, or we can say that rho v naught is 36 rho v is 36% of rho v naught. Rho v is equal to 36% of rho v naught. This is at the relaxation time. So that is why from there we got this value 36.8% of the initial value. So we can say rho v is equal to rho v naught into 0.368, or rho v is 36% of rho v naught. Okay, so this is the case for the relaxation time. So it shows for the good dielectrics the relaxation time is very long, that introduced charge remains whenever placed for the times up to days. But when we have the conductors, so for that good conductors, the relaxation time is so short, in seconds, in microsecond, milliseconds, like that. Means 10 to the minus 19 seconds, right? So it is very less than the microsecond as well, nanosecond as well, right? So for the quartz or the insulators, the relaxation time is more as compared to the conductors, because we know this formula that TR is equal to epsilon upon sigma. So as the sigma is very large, so when sigma is large, then TR will be less, right? So these things you have to take care about that. Okay, so I hope this point is clear to all of you and you understood very well about this topic in the electrostatic field. Thank you very much.